As we get into chapter 5, we start looking at the reverse process of taking derivatives. It's called, one way of calling it is the antiderivative. Um, it has several uses. We're going to be exploring those as we go through chapter 5. I'm not going to go into it too much here. So, basically, an antiderivative is also known as something as an integral. And we're going to kind of walk through how to go through and do these antiderivatives or integrals on this. One of the things that you have to keep in mind is when we're doing an indefinite integral, which is what we start off doing, and we will talk about a definite integral as we move into more or less section 5.3. When we take an antiderivative or we do an integral, the fact of the matter is, if I look down here at the bottom, right here, each one of these, if I took their derivative, would be 2x. So if I take the antiderivative of 2x, I'm going to get x squared, but it could actually be any one of these three things. Or more, I mean, those three things and an infinite number more. So what we have to make sure to do in those instances where we're taking an indefinite integral is that we have to make sure that when we answer the question, when we say what the antiderivative is, we have to signify that there could be possibly an arbitrary constant c that follows your expressions with x. So, so if you were asked to do the antiderivative or the integral of 2x dx, the dx is kind of an indicator that you had once taken a derivative of this. So the function that you had here, was the result of a derivative, which means the function you should end up with is a differentiable function. So when we do that and we get the x squared, we put the plus c there to indicate that there could be any number of constants that followed that x squared and would have produced the exact same derivative to get to 2x. So, in a definite integral, usually just called an integral, it can be checked by differentiation. So, if you get if you do the integral of a function, you get, another function plus c, you take the derivative of that, treating c as a constant, you should get back the original what you started with. So, and what you're going to see a lot of times that we do integration is that we do have derivatives being part of the process. So, derivatives aren't going away. It's just, as we do some of these techniques of integration, there's going to be sometimes we do employ derivatives, but you have to remember we are doing essentially antiderivatives, and you can't confuse the two things. And that's where a lot of students will sometimes have difficulty with these things. Now, there are some basic rules for integrating functions. The first one is that there is a power rule for integration. So if I'm taking the integral of x raised to the n power dx, I'm going to basically add 1 to the exponent. If you remember, we did the derivative, we subtracted 1. Or we would actually multiply by the original exponent and then subtract the exponent by 1. Here we add 1 to the exponent and then we divide by the new exponent. This will work for all circumstances except when n equals -1. And we'll talk about what happens when n equals -1 momentarily. This is just a wording of what that was. So an example, if I wanted to do the integral of the square root of x dx, and always keep in mind that these two things, this symbol here and the dx or dt or whatever variable you're dealing with, that they come together. That's like one big symbol with the expression you're taking a derivative of smashed between them. Okay. First, what I'm going to do is I'm going to, like we did with the derivatives, is I'm going to treat the square root of x as x to the 1/2 power, and then I'm going to employ the rule. So I'm going to add 1 to that exponent. 1/2 plus 1 is 3/2, and now I'm going to divide by the new power. 1 divided by 3/2 is 2/3, so I get 2/3 x to the 3/2 power plus c. Now there's other ways you could write it. I mean, you could actually write this as 2 square root of x cubed over 3 plus c. There's different ways you could write the answer, so keep that in mind. I mean, sometimes different formats might be used. And you just have to make sure you realize that if it's just a formatting difference, then you might have the same answer as what the book is showing. So now it's your turn. I want you to take the integral of dx over x cubed. So we have a circumstance right here. We have dx over x cubed. Well, x cubed in the denominator does mean that I'm going to have the integral of x to the negative 3 power dx. That's the same thing. So if that is the same thing, what I can now do is I'm going to add 1 to the exponent. Negative 3 plus 1 is negative 2. And now I'm going to divide by the new exponent. That takes care of the integral of that. Now I have to put an arbitrary constant c at the end to indicate that I can have a multitude of different answers. Now that's an acceptable answer. I can rewrite this as negative 1 over 2x squared. That's another way of writing it. And that's more of a simplified version of it, so that might be the more common way you would tend to see that answer. Integrating 1 or any constant. I mean, integrating 1 or any constant, basically the whole premise behind it is I have, if it's 1, I have x to the 0 power. I'd still use the power rule for integrals. I'm going to add 1 to that exponent, and I'm going to now divide by the new exponent of x. So, I'm going to basically have x plus c. It works the same way basically if I have a constant multiple in front too. And I'll show you how we handle constant multiples in a moment, because we kind of just ignore them like we kind of did with derivatives, and then we bring them back in when it's time. There's also a rule for adding and subtracting integrations, but basically it's very similar to what it was for derivatives. If I'm doing an integral of 2 or more terms being added and or subtracted, I can separate it into multiple integrals being added and subtracted to each other. So basically it means I could take each term, take that integral, and then, add or subtract or combination all together. So for instance, if I was doing this integral here, I could think of this as the integral of x squared dx plus x cubed dx. Now as we go through and do these integrals, we don't put a plus c in for both of them, because one arbitrary constant plus another arbitrary constant is going to give us yet another arbitrary constant. So we could assume that, if there's any constants that would be the result of the first integral and any that would be the result of the second interval, they would combine together, giving us yet another constant, which is, again, arbitrary. So the integral of x squared dx is x to the 3rd power divided by 3 or times 1/3, whichever way you want to accept it. And the integral of x cubed is x to the 4th times 1/4. You could also, again, think of them as x cubed divided by 3 plus x to the 4th divided by 4th plus c. It really depends on the textbook you're looking at, who writes it. That's how it's handled. Constant multiples. If I'm doing an integral and I have a constant multiple, sometimes I might want to keep a look at it and see what that constant multiple is, because I could think of it as, okay, well, if I had like 3x squared, well, I know that's the derivative of x cubed. So if I do the integral of 3x squared, that's going to be x cubed. I don't have to really do anything. It's just kind of me reversing my derivative rule. If I would have something else in front of the x squared, like a 9 or a 7 or something like that, then I may want to factor it out and handle it the proper way. So for instance, if I was doing the integral of 6x squared dx, I could just factor that constant multiple out and just do the 6 times the integral of x squared. I can then do the integral of that, and the integral of 1/3, x squared is 1/3 x cubed, plus some arbitrary constant c. Now, again, technically I should really multiply that by 6, but again, 6 times an arbitrary constant is just going to be yet another arbitrary constant. But as far as the 6 times 1/3 x cubed, that does simplify further because of the fact that 6 is a multiple of 3, so I end up with 2x cubed plus an arbitrary constant c. Which gives us this rule here. If I just have the integral of a constant, it's just going to be that constant times x plus c. Again, it's from the same basic rules, that we just kind of went over. So with these rules and these examples we just did now, I want you to try and take the integral of this function here. So with this function here, again, I can think of this as being the integral of 12x cubed dx plus the integral of 3x squared dx minus the integral of 5 dx. I'm going to move the constant multiples out. Now, if you know how to work your derivatives in reverse and say, like, well, what would I have had to get 12x cubed? I had to have an x to the 4th, and I probably would have a 3x to the 4th because, I would have, So I could probably know that that's from there. I'm going to do that in several steps to still get to the same answer. But if you recognize things like that, you're more than welcome just to, making sure that you're right now. Just handle it that way instead of doing extra steps to do it. I'm just going to leave this alone because we actually do have a rule just for a constant. So for this, I'm going to end up with 12 times x to the 4th over 4. So I basically add 1 to the exponent and divide by the new exponent. Same thing here. Now I do the integral of that. That's just a constant, so I end up with 5x plus c. And now I simplify. I end up with 3x to the 4th plus x cubed minus 5x plus c. Now let's move on to the next one. I want you to try this integral, the integral of 4 over x cubed plus the square root of x dx. So for this one here, I want to think of this first. I'm going to make these powers of x that are just a little bit easier to deal with. So I would get the integral of 4x to the negative 3 power plus x to the 1/2 dx. I can now think of these as two separate integrals. Now, once you get the hang of doing these, you don't necessarily have to write out every single step along the way. But wait until you actually do get the hang of doing these first. Don't just start skipping steps before you've gotten a good handle on it. I can usually do these without doing as many steps. I'm sure your TAs can, and they probably will at times, skip some steps. So if there's some things that you're not quite getting, even from me, because I may skip a step or two if I'm explaining a problem in class, or one of your TAs is, make sure to ask us to go back and try to fill in some of the missing information. So I basically factored the 4 out of the first one because I can. And so now I'm going to have 4 times. Now I'm going to have x to the negative 2 power because I'm adding 1 to the exponent. Make sure you handle your negatives correctly. And I'm going to divide by the new exponent, which is negative 2, plus x to the 1/2. I'm going to add 1 to that. That's going to be x to the 3/2. And I'm going to divide by the new exponent. That's over 3/2. And I'll simplify that momentarily. And now I can just put an arbitrary plus c at the end because I've done all the integration. Here I'm going to have essentially negative 2 times x to the negative 2 power. And I could leave it like that, and I'm going to rewrite it in a second as well. Dividing by 3/2 is the same thing as multiplying by 2/3, so I could write this as 2/3 times x to the 3/2 power plus c. And again, there's different ways I could write the final answer for this. Just keep that in mind because as you go through and do it, you may see different versions of it. So for instance, I could call this -2 over x squared. I can call this 2 times the square root of x cubed all over 3 plus c. So there's different variations, but all these would be acceptable answers in this kind of circumstance. For this one here, find the integral of x squared times x plus 6 squared dx. We don't really have a formal multiplication and quotient rule for integrals. That means that oftentimes if we're given an expression that we want to take an integral of, and there's multiplications and divisions involved, what we're going to need to do at times is we're going to need to simplify it first and then take the derivative, or antiderivative, sorry. And we would kind of do the same thing at times with derivatives too, when it was feasible to do it. If I had x squared times x plus 6 quantity squared, and I was asked to take a derivative of it, x plus 6 squared is not extremely hard to do. Then multiplying that answer, everything by x squared is not hard to do. So it would be probably more of a quicker thing to multiply that out first and then take the derivative. But if it was like x squared times x plus 6 to like the 50th power, that's a different story. And we're going to have circumstances like that with integrals as well, just not quite yet. And there's going to be other methods we could possibly use. We use substitution, we use integration by parts. There's other methods of integration that we can use at those times to try to deal with those circumstances, depending on what we have in front of us. But for the time being, if we encounter a situation like this, we're going to simplify first. So the first thing that's done here is the x plus 6 squared is expanded. So I would take x plus 6 times x plus 6, and I would end up with x squared plus 12x plus 36. I would then distribute the x squared, and I would end up with the integral of x to the 4th plus 12x cubed plus 36x squared dx. And now I'm just going to do the integration like I normally would. I would get the 1/5 x to the 5th for x to the 4th. I get the 12 times 1/4 x to the 4th for x cubed. I'd get the 1/3 times x cubed for the x squared, and the plus c, comes at the end because I could have an arbitrary constant at the end. And then I could do some simplifying, especially for the terms that I can combine a little bit, and I end up with this expression here. So if you're given something that involves multiplications and or divisions, you want to simplify first. So with that being said, give this one a try. So for this one here, I'm going to do kind of the same thing that we did before. I'm going to FOIL at the top. And if I do that, I'm going to end up with 6x squared minus 8x plus 9x minus 12. The minus 8x and the plus 9x I can combine, and I'll do that momentarily. I don't know why I got the extra line there, but you can still see everything, so I'm not going to worry about it. So I'm going to end up with 6x squared plus x minus 12 all over 2x. And I'll actually carry out the division with the 2x. So 6x squared divided by 2x is 3x. X divided by 2x is essentially 1/2 x. Or just 1/2, sorry. No x, just 1/2. The x's cancel. And the minus 12 over 2x, I end up with a minus 6 over x dx. And this one here, I probably got a little bit ahead of myself because there's going to be, I'm going to, in the next section we are going to handle a circumstance here, because one circumstance here we're not going to be able to handle quite yet because we haven't talked about it yet. But let me go through and do this. 3 times the integral of x dx plus the integral of 1/2 dx minus 6 times the integral of 1 over x dx. Now, just so you know, this one here, not a big deal. I'm going to have 3 times x squared over 2. This one here, I'm going to have basically 1/2 x minus 6 times. Now, here's where we're going to run into a difficulty. This is like having x to the negative 1 power. We don't know how to handle that yet. This was, I made this example and then didn't notice that until as I was doing this problem in particular. And remember, that exponent rule does not work on instances where I would have x to the negative 1 power. And the reason being is that the integral of 1 over x, if you think about it, well, what did we get? When did we get 1 over x when we took a derivative? Well, that happened when we were doing the natural log of x. And so what we would have to do for this part is say the natural log of the absolute value of x. We'll get into that later. And then I would do the plus c. So that part in red we have not handled yet. We have not talked about it yet, but we will momentarily. So basically 5.4, 5.5, 5.6, that stuff gets mentioned. So, but just to finish this out, 3x squared over 2. I'll just write this as x over 2 minus 6 times the natural log of the absolute value of x plus c. So part of this you would not have been able to do very well yet, but we will as we go through the subsequent lessons. So one of the things that you could possibly do now is, if you remember, when we had a cost function, we would go to marginal cost by doing a derivative. Well, now if I know the marginal cost, I can now go back to a cost function. And what's going on with this particular problem here is they say, okay, a company's marginal cost function is, and they give you MC of x equals 6 times the square root of x, and the fixed cost is $1,000. Now, the fixed cost is basically the cost when no units, when x is 0, essentially. So what they're doing here, and the reason why they're telling you that, is they're taking the arbitrary constant c and giving you a value so you can actually evaluate what that is. So as we go through and do this, I know that the cost function is going to essentially be the integral of the marginal cost. So I'm going to integrate 6 times the square root of x dx. And of course I'm going to factor out the 6. I'm going to think of the square root of x as x to the 1/2 power. So now when I take that antiderivative, I'm going to end up with x to the 3/2 over 3/2. And dividing by 3/2 is the same thing as multiplying by 2/3. So this all becomes 6 times 2/3 x to the 3/2 power. They put plus k here to avoid confusion with c for cost. I mean, so they're putting an arbitrary constant at the end. They just don't want to put a plus c there, because they don't want you to think that C at the end is the same thing as the C you have on the left-hand side. So they're just putting another letter in for the arbitrary constant. So if I simplify that further, I get 4 times x to the 3/2 power plus k. So we still have to find the value of k. We know that the fixed cost, when everything is 0 is going to be, now they're saying that C of 0 equals K. That's not necessarily, the fixed cost is going to be C of 0, but C of 0 does not necessarily mean that K is going to necessarily be that. That's what it is here, because when I put 0 into the function we got, all I'm left with is K. And that's because, again, since we had that C of x was 4 times x to the 3/2 power plus that constant, when I do C of 0, I'm going to end up with 4 times 0 to the 3/2 power plus k. So yes, in that instance it does equal k. And since we're saying, well, C of 0 is supposed to equal 10,000, it stands to reason k has to be, or 1,000, sorry, 10,000 is a little bit too high. Since k had to be 1,000, That's because C of 0 had to be 1,000. So the actual cost function is that. It's not always going to work that way. It really depends on the the function that you're working with. If you plug 0 in and it doesn't all come out to be 0, then your arbitrary constant may not necessarily be the value they're giving as the fixed cost or the starting point or whatever the case may be. So as far as simplifying integrals, integrate the marginal or rate of change. That's what you're basically doing when you're doing integration. You're usually taking a rate of change and trying to get back the whatever it was to begin with. So if it's a rate of change dealing with distance over time, then you're going to be getting a function back that gives you the actual distance at a certain time, not the change in distance. To evaluate the constant c, you want to evaluate the integral at the given number, usually at t equals 0 or whatever the case may be. They'll tell you what that is. Set the result equal to the stated initial value. You solve for c. Don't always think it's a replacement. They say the fixed cost is this, or at time 0 it was equal to this amount. It's not always going to be what that's not always going to be what the arbitrary constant is. So your turn. A $20,000 art collection is increasing in value at a rate of 300 square root of t dollars per year after t years. Find the formula for its value after t years, and then find the value of the art collection after 25 years. So let's break this down into two parts. I want you to first find the formula for its value after t years. So I'm going to let v stand for value, and the value function I'm trying to get based off of time t should be the integral of this rate of change. dt. Okay, so now again I'm going to think of this as the integral of, I'll move the 300 out here, t to the 1/2 power dt, which gives me 300 times t to the 3/2 divided by 3/2 plus an arbitrary constant c. And so when I work this out, I'm going to end up with 200 t to the 3/2 power plus c, which I could also think of as 200 times the square root of t cubed. Yeah, I hate when that happens. T cubed plus c. Now the thing is, again, I'm looking for the arbitrary constant. So we were told that it started as $20,000. So that means that's what it was worth when it was bought. So no time has passed. So I know that v of 0, which would equal 200 times the square root of t cubed, or 0 cubed now, plus c should equal 20,000. Now in this case here, since I am doing 200 times the square root of 0 cubed, that all becomes 0, so it stands to reason that we now know that c is 20,000. As I said, it doesn't always have to be that way, so don't assume it. The moment you assume it is the moment it's going to blow up in your face and you're going to find out it's not the same thing. So the function v of t that we're actually looking for and that we want to use for the next part is going to be 200 times the square root of t cubed plus 20,000. Now with that being known, part B, find the value of the art collection after 25 years. So for this one here, this one should be more, up your lane, but definitely it's not anything new because you've done this since algebra days. Knowing that t is 25 years and knowing that, the function was made with t being in years, this is essentially asking me to find v of 25 at this point. So all I have to do is go to the function I just found the formula for. And I'm just going to replace t with 25. And when I do that, I get basically 200 times 125 plus 20,000. So it ends up being the grand total of $45,000. So after 25 years, if that is indeed the function that describes the rate of change in the value of the painting, in 25 years it should now be worth $45,000. Moving on, some additional rules. This one here, they actually introduced it a little bit earlier than I've seen in most calculus books. Being able to differentiate e to the ax power. Usually they would have you learn how to do e to the x power because the integral of e to the x is just e to the x. It's because that's what the derivative was. And this process here of getting this formula would actually be from us using a method that we're going to be looking at as we end unit of chapter 5 here, called integration by substitution. But they give us this formula to make use of right now because you are going to encounter situations where e might be involved. So the integral of e to the ax power is just going to be 1 over a times e to the ax plus c. This is a formula that you can eventually not even worry about once we get to lesson 6 in chapter 5. Because if you just know that the integral of e to the x dx is e to the x plus c, which is just basically kind of reversing what the derivative had done, integration by substitution will produce the results that this formula gives you. So I'm actually kind of surprised they introduced it this early. I'm not used to that, but that's the way it's introduced in your business calculus book. So let's have a look at a couple of examples where they make use of this. So if I have e to the 1/2 x dx, that's the same thing as me having 2 times e to the 1/2 x plus c. The reason being is that, 1 over 1/2 is 2. And they give you the rationale over there. If I have the integral of 6 times e to the negative 3x, I can move the 6 to the outside. I'm going to look at a equaling negative 3 for this. So when I integrate that, I'm going to end up with 1 over negative 3, which is negative 1/3 times e to the negative 3x. And then when I do some simplifying, I end up with negative 2 e to the negative 3x plus c. And of course, as I mentioned before, the integral of e to the x dx is just going to be 1 times e to the x plus c. That's really it. And that is the actual rule. This other rule, they make it sound like in this textbook that the first rule is an immediate consequence, or this rule is an immediate consequence of the first rule, the integral of e to the ax. When in actuality, in most other textbooks, it's presented the other way around because the e to the ax rule comes about from the process of integration by substitution. Your book kind of reverses that a little bit to kind of get the e involved a little earlier. So with these things in mind, I want you to try to take the integral of this. So for this here, I'm doing the integral of 24e to the negative 2x over 3 plus 6x squared dx. So now again, I'm going to write this out a lot more thoroughly than a lot of you may do. I'm going to change that to a negative 2/3 times x. I move the constant of 24 to the outside. Dx plus 6 times the integral of x squared dx. So for this one here, I'm going to have 1 over negative 2/3. Now, that means 1 over means reciprocal, so I'm just going to do negative 3/2 e to the negative 2/3 x plus 6 times x cubed over 3 plus c. When I work this out a little bit, I'm going to get negative 36 e to the negative 2x over 3. I can put it back in that format, plus 2x cubed plus c. Here now we're coming to what I mentioned earlier. If I do the integral of 1 over x, or essentially the integral of x to the negative 1 power dx, same thing. I get the natural log of x. Now, they don't put the absolute value around it, but the thing is, they explain as we go into this why it's an absolute value, because, you know, essentially we can't have negatives in there. It's restricted. So, you know, we put the absolute value in there to make sure it was a differentiable function, as a matter of speaking. So that's the official rule for 1 over x dx. Sometimes it is expressed looking like this, right here. Sometimes it's expressed looking like that. All these are the same thing. They all produce the same integral value. So with that in mind, tell me how you would do the integral. Well, right here, it's not your turn yet. Let's walk through this one. I have 5 over 2x dx. Well, I could look at this as just being 5/2 times 1 over x dx, and I could move that 5/2 out to the outside. So now I know that the integral of 1 over x dx is just the natural log of x, absolute value of x plus c. So that's the final answer. And now they incorporate this into a new power rule for integration. If I have x to the n power dx, as long as it's n is any number except negative 1, I'm just going to do the 1 over n plus 1 times x to the n plus 1 plus c. If it equals negative 1, it's going to be the natural log of the absolute value of x plus c. We don't usually state it that way, but they're just kind of combining them together for the heck of it. So with what we just talked about, your turn. I want you to find the integral of this. Much like the problem we just got done doing, I could think of this as 1/3 times dx over x, which is one of the formats we saw in that formula. And so I have 1/3 times the integral of dx over x, which is the same thing as 1 over x dx. So I'm going to end up with 1/3 times the natural log of the absolute value of x plus c. Excuse me. Now it's your turn for this one. So for this one here, I'm going to do a few things. I'm going to kind of do it all in one step though. I'm going to move the 3 out to the outside and just have the integral of e to the 2x dx for the first term. I'm going to keep this as is because I know that 3x squared was the derivative of x cubed. And so I know when I do the integral of this, it is going to go to x cubed. This one here, I'm going to have 3 times the integral of 1 over x dx. And here I'm going to have 3 times the integral of x to the negative 2 dx. So now I'm going to take these integrals. So according to the rule we have for e to the 2x, or e to the ax I should say, I'm going to have 1/2 e to the 2x for that. For this one here, since I said that I knew that 3x squared was the derivative of x cubed, then the antiderivative of 3x squared is just x cubed. It's going to be one of those days, it looks like. Plus 3 times, well, the integral of 1 over x dx is the natural log of the absolute value of x. And then 3 times, well, now I'm going to take x to the negative 2. I'm going to add 1 to the exponent and get negative 1. And then I'm going to divide by negative 1. So now when I simplify, I could write it like this. There's different variations of how you could write it. Like so. Well, that's going to become a minus because I do have a negative in there. So let's get rid of that and put just a minus sign there. Minus 3 over x, and I could put the plus c at the end. Actually, technically, I should really have it up there too. But so long as I produce it at the end, the better. I mean, so just have to make sure I know it's an arbitrary constant being shown there. They go into specific examples of where this could possibly use. You know, they talk about consumption of natural resources, and give an example here. You know, the annual world consumption of tin is predicted to be 0.26 e to the 0.01 t million metric tons per year. So they're giving us a rate of change where t is the number of years since 2008. Find a formula for the total tin consumption after t years of 2008 and estimate when the known world reserves of 6.1 million metric tons will be exhausted. So basically, they're giving us a rate of change. They want us to find a formula that tells us you know, how much has been used by a certain year. So what I'm going to do is I'm going to take this and I'm going to integrate it. And when I integrate that, you know, I'm going to factor out the 0.26. I'm now going to employ the e to the a x rule, or in this case e to the at rule. So I'm going to end up with 0.26 times 1 over 0.01, which is 100, times e to the 0.01 t plus c, which gives me 26e to the 0.01 t plus c. Now, the fact of the matter is, the total consumed in the first 0 years must be 0, because we haven't consumed any yet, okay? Or nothing was consumed. I mean, all the measurements were taken, so anything that was consumed beforehand, we're not even considering anymore at this point. So, in this case, it's c of 0 equals 0. Well, for c of 0 to equal 0, I got to take 26e to the 0 power plus c. E to the 0 power is 1, so I got to get 0 to equal 26 plus c, which means c has to be a minus 26. So here's one of those instances that, you know, your starting amount or the value you get at c at 0 for c is not the constant. So this is the formula. And now we want to look at the consumption, or when this will be exhausted. So I'm going to set this equal to 6.1. And I'm going to solve. So I'm going to do add 26 to both sides, divide by 26 on both sides, natural log both sides, and then divide by 0.01. So basically, you know, if it continues at that rate of change, in about a little after 21 years after 2008, the world's tin supply will be exhausted. But basically, I mean, it's not just for consumption problems and things like that. This is an instance of, you know, given a rate of change, you're looking for the original function and to answer questions about that. So this one's going to be very similar. A biotechnology investment originally worth $30,000 grows continuously at a rate. So they're giving you the rate, so you don't have to worry about, you know, using, you know, any of the compound interest formulas that we talked about earlier. So 1200e to the 0.15 t dollars per year, where t is the number of years since the investment was made. What is the value of the investment after t years? So the first part of this is that you're going to need to find a function that tells you the value of the investment given time. So what is it that you have to first do to start working towards this? Well, the thing I have to do is, since I'm basically given that the value again of this stock or the investment, the rate of change for that is 1200 e to the 0.15 t. Well, for me to get to a formula for v of t, I'm going to have to do an integral of this. So I'm going to integrate this. I'm going to move the 1200 up front. So again, I'm showing more steps. I sometimes will start skipping steps, and once you get the hang of knowing what needs to be done, you can certainly do so yourself. I'm going to get 1 over 0.15 e to the 0.15 t plus some arbitrary constant c. And when I evaluate that, I end up with 8,000 e to the 0.15 t plus c. I don't have the entire function yet. I need to figure out what c is. So what I want you to do now is figure out what c is supposed to be. Again, a lot of students make the mistake. They think, well, the original investment was $30,000, so the original amount, $30,000, is what the constant should be. And in many cases, yes, that would be the case. But all we know from the information we were given is that v of 0, which equals 8,000 e to the 0.15 times 0 plus c should be 30,000. Well, that basically means that I have 8,000 plus c equaling 30,000, which means c is going to be 22,000. So c actually equals 22,000. So my formula that I needed to get for this is 8,000 e to the 0.15 t plus 22,000. Now that I have this, I can now figure out what the value of the investment will be after 10 years. So what is the value of that investment? Well, all I have to do left for this is just plug in the 10. And when I plug that 10 in, I end up with approximately $57,853.51. So that's what the investment would be after 10 years, what it would be worth. So, and that is the last example I have here for this portion of it. If you have any further questions, make sure to ask about them in class. Also make sure you move on to 5.3 and then do the exercises. I'll see you in class.